Hello, good morning. It's Anagon Live, and it's for me still day 16 of Advent of Code. Wow, this was a very hard puzzle, and I was able to finish part 1 on the stream yesterday, but part 2 I still haven't done yet. So I'm going to try to actually get part 2 done before day 17 starts. So wish me luck. I have not very high hopes for it because it's very numeric and algebraic, and that's not my strong side, but I'm gonna give it a go and see if we can actually get it done and get the right answer. And if not, yeah, I will probably continue some other time during the day and maybe ask around for some tips here and there how to solve it. So if you haven't worked on day 16, I'll give you a quick introduction to what we are supposed to do, and that will also help me to actually get a good mental picture of what we need to solve and how to perhaps solve it. So day 16 is very numeric. It's called Flawed Frequency Transmission, FFT, which of course is a hint to fast Fourier transformation. A fast Fourier transformation is a transformation that takes a signal and then extracts from that all the different frequencies in that signal and the phases of those frequencies, and the amplitudes, of course. And I'm not sure if what we're doing here in day 16 is exactly the same as that. I kind of hope it is, because being able to implement your own fast Fourier transformation, that is pretty awesome, I would say. It is handy for so many things like line detection or frequency detection. It's useful for noise cancellation and many other applications that I'm not aware of right now. So what I'm going to do is I'm going to draw a little bit about this puzzle and see if I can make it clear. So what we're dealing with is an input list that has a lot of digits. So for example, let's say the input list is 98765. That means that it's a list of those 5 digits, so you can consider it as separate items. It's not really one huge number. Then we have a base pattern. A pattern is a list of digits that we're going to multiply each element by, and the base pattern is 0, 1, 0, minus 1, like this. And then to apply the transformation, we're going to apply something to these numbers and then produce a list with the same length. So we get again several numbers here, and then we're going to apply the same function again, and we're going to do that for 100 times. And then at the end we do get a number with the same length, and we have to provide the first 8 digits of that number and what that is. So what transformation do we actually need to apply? What we need to apply is we need to basically give a weight to every item in the list and then add them all up. And the weight is based on the base pattern, this one right here. Let me just write it down. But that is the base pattern. That's not the actual pattern that we're going to use while we're weighing and summing those numbers. So how it works is that you have to repeat the base pattern for every digit in the input. So we have 5 digits, and for the first digit that means that the base pattern is going to be just the way it is written in the base pattern. So the first item in the pattern is 0, then 1, 0, then minus 1. But for the second item we're going to repeat every digit twice. So that base pattern is 0, 0, 1, 1, 0, 0, minus 1, minus 1, and so on. For the third item we're going to repeat it 3 times, like this. 1, 1, 1, and then we get zeros, and so on. Now you see that the third item has more digits in the base pattern, or in its pattern, than the one on the left, and that is because we are actually going to repeat it. So from the point that you've used up all of the numbers in your pattern, you're going to repeat it. So you would just basically get the same pattern here again. So that's what it looks like. Right, like that. And so on. So that means that all of them will start with zeros. If you would repeat it 4 for the 4th digit and 5 times for the 5th digit, then you would see also that basically what you see is a kind of certain shape here with a lot of zeros that is ever incrementing, and I think this is going to be important in solving the puzzle, but I'm not entirely sure yet how we can use this. Then the last little bit of modification we need to do is we need to actually ignore the very first item in the pattern. So that's this line here, we're not going to use that. Okay, so how does it work when we're going to multiply our digits and add them? So 9 is going to... Wait a second. So we have 9, 8, 7, 6, 5. Those have positions, those numbers. It's 0, 1, 2, 3, 4. And so let's start with position 0. To add that, to calculate the new digit for position 0, we're going to multiply 9 by the first value in the pattern for the first digit. That's here. And then, so let me see how I can visualize that. So 9, the one that goes here, that is basically a sum of 9 times 1 plus, and then 8 times the first digit for the second pattern, 0, plus 7 times, and then the digit for the third one, for 7, that's also a 0. I start to realize something here, maybe. 0, and we adding also 6 times 0 and 5 times 0. So now we've used all of these patterns. And then the answer is that for this first digit we get 9. Now for the... hold on a second. No, I'm actually not explaining it correct entirely. We are not going to look right over those patterns. So the way I showed it here was not correct. For the first digit we actually use only the pattern for the first digit. So 9 times 1, that was correct. We multiply the first digit with the first item, but then we multiply the second digit with the second item in the pattern for digit 1. So then the sum would be 8 times 0, then plus 7 times minus 1, plus 6 times 0, and then plus 5 times 1. So you can calculate that. So it's 8 plus 0 plus minus 7, so that's 2, plus 6, that's 8, plus 1, that's 9, so we get 9 as a result. And for digit 2, or in my list it's called digit 1, so the second digit, you get something similar. So that would be... so then we're going to look at the second pattern here. So for that you're going to use 9 as well, multiply by 0, then we're going to take 8 and multiply by 1. So now we've done those two, plus 7 multiplied by 1 also, multiplied by 1, plus 6 multiplied by 0, plus 5 multiplied by 0 also. So what do we get then? We get 8 plus 7 plus 6 no 6, it's multiplied by 0. So it's 15. And now there's a last rule, and that is that when you have digits that are numbers that are more than 1 digit long, you're only going to take the last digit. So in that case, it means we're going to remove the 1 here. So this was actually 15. Just make a tiny note. Maybe that's very tiny actually, like this. And so we can continue doing that for all of the other numbers. And then once that is done, the whole cycle repeats. Now, our input that we received for part 1 was, let's see, I'll show you on my screen. It was this number here on the top. You can see it is kind of long. It is 650 characters long, so that means that in our diagram the list here just goes on for like until character 650, so it's very long, and it did take some time to calculate. I can run it and show you also how long it takes. So what we just showed here was actually a phase, and so we're going to do 100 phases and then see what we get out of that. So you see it's still running phase 1. I think it's actually running more slow because I am already working on part 2. And in part 2, what we did was we actually multiplied our list. So I'll remove that multiplication, and then you can see that phase part 1 is not that slow, in fact. So my answer was... Okay, I see that my answer is not correct anymore, and that's probably because I'm overriding something, which I am. Rerun it again. Yeah, okay, now you can actually see that it's going over those phases step by step, and it does take a bit of time, but it's not too bad. So after calculating 100 phases, we get another output list, and we need to provide the first 8 digits of that list. And that was this number, but I think, no, that's not the number I actually got in the end. So I'm not sure exactly what I changed. Oh yeah, there was another addition to part 2, and that is kind of changing my output at the moment. So I'll go over what the changes are for part 2. So for part 2, mostly there were 2 changes. So our input list looked like this at first, but now there's an extra change that the input list is going to be repeated 10,000 times. So that means that it grows like this, multiplied by 10,000. So 10,000 times the length of the original list. That is really insanely huge. The original list was already quite big. That means that we actually have 650, I think 6.5 million items in the list. So that's 4 for the repetitions and 1 0 for the original length. So we should have 5 zeros here, and that is actually 6.5 million items. So what it means is that doing this calculation where you kind of take from each item in the list one and then add it to another one multiplied by something, and then going over and over and over and over, and when you're finally done reaching the end, you've only calculated the first character of your new list, and your new list is of course super long, so that would take forever. And you can see that in fact that I tried it on a small example input, and let's run it with 10,000 repetitions. And I ran it for a few minutes and not even a single phase was completed. So yeah, you really cannot just force it. And this example has only 32 characters, so 32 digits, while the real input is going to have 650 multiplied by 10,000. So brute forcing this or just naively implementing it is definitely going to be impossible. It's going to take probably more than a lifetime to complete. So we need to come up with a faster way to make all of those calculations. And now I don't have a solution right now. And what I'm going to try to do is to draw out the additions and the multiplications and see where I see repetitions, where I find a pattern that is repeated or some calculation that we are repeating. And to do that, I want to start with an example input that is a bit smaller even than the first example that I showed. So let's start with an input that has only 4 digits, and I will use 5, 4, 3, 2 for that, and we'll have a base pattern the same as before of 0, 1, 0, minus 1, and so we can repeat those patterns from the previous slide. So that will be 1, 0, 0, 0, and here will be also, hold on a second, yeah, we've skipped the first 0, so that is correct. Yeah, so basically it's like this, 1, 1 at first, and then for the second one we have 2 1s, then it looks like this triangle. Here we have 3, and here we have 4, and then after that follow the zeros, 2 zeros here, 3 zeros here, and 4 zeros here. Yeah, that actually doesn't fit, but I hope it won't matter that much at the moment. And then we get the minus 1, and then we get another 0, and then this one repeats, so that will just be 1, 0, minus 1, 0, and another 1. Now let's try to visualize how we're actually adding all of those numbers. And normally what I'd like to do in these kind of formulas is to use colors for each variable and then show you which variables you're using for every part. So maybe what we can do is actually give them names instead of using colors as a coding. So let's call, let's see how we can call it. We can call this one A, for example. Maybe we can give every element in a pattern a name, like A0, A1, A2, A3, A4, and that means that we have row A, B, C, and D, or column A, B, C, and D. Maybe that will help. And then let's see what we can do. So every digit will have its own letter. Yeah, and so let's say that A just represents the digit. And then we have, of course, iterations. Wow, okay. Well, let's see if that helps us get anywhere closer. So the first phase will look like this. We have A, B, C, and D. That is phase 0. And phase 1 is basically yeah, we need to compose those digits separately. That is a bit annoying. We cannot just like say it's A plus B plus C or something like that, because that would create one huge number, and well, not huge, in fact it would be a few digits, like maybe a few more than 5, but that doesn't work. We have to calculate every digit separately. So it's rather that we have here a digit and another digit and so on. So the first digit will be calculated like A times, how is it? So we're looking at the pattern A times A1 plus B times, hold on, it's A0 actually. And now I'm thinking, should we actually call the first element A0 or A1, because we were told to skip one item from the pattern list. So the first item is basically the row with only zeros, and maybe it makes sense to call that one A0, and use A1 for the next one. So we call that one A0 and the rest will just keep going. And now what is interesting is that the number here is actually A1 again. Basically it's the same as A1. And here we have A2, A3, A4. But that's not the case for B, because the B column will have a pattern that repeats every 8 times and not every 4 times. So I'm not sure how that's going to look in our formula. We might not be able to see a pattern because of this, but let's just see where it goes. So we multiply A by the first item in the A pattern list, and that item is A1, and then we add to that B multiplied by A2, then we add to that C multiplied by A3 plus D times A4. Okay, so that's that. We could also visualize that as a matrix actually. So we have a matrix like A, B, C, D, and we have A0, A1, A2, and A3, and actually A4 is also part of this little game. And so how we multiply it is basically like this. Excuse me, the A0 is skipped, so that one is not used. And then the matrix looks like this, and all the other ones are going to be empty. So when we multiply this matrix with all the A values, then we actually get the calculation for phase 1. So it is an identity matrix. Is it an identity? No, it's not an identity matrix because we have one extra row, but you could also say that you just ignore it because you don't take it into your calculation. So it is an identity matrix, and I'm not sure in what way it really helps, but I just consider it a possibly relevant bit of information. Let me just keep it somewhere. Hey Alex, good morning. I just woke up and I'm trying to wrap my mind around part 2 of day 16 still. And I feel like this is a matrix problem actually, or some kind of numerical trick problem. And yeah, at this point I'm just trying to figure out if there are any patterns in the way we add the numbers for all of those phases, and if there are any patterns or any repeated parts that maybe we can store intermediate results or something and reuse those. And so far, yeah, I'm just going through it quite slowly or steadily, and I haven't found a pattern yet because I've only looked at the calculation of a single digit. So phase 1, the first digit will be as described right here. And now we will look at the second digit. I'm just going to remove all of these parentheses and this comma. Let's see how I can visualize it even more compact. Not entirely sure. Maybe I was thinking if we can somehow also put this modulo in the matrix. Hey Nubali, good morning. How are you doing? You did manage also part 2 for yesterday. How did you solve it? Oh, I'm not asking for a solution, but like, did you use some kind of mathematical theory that you knew, or just kind of playing with numbers, or some code optimization? I'm curious in what kind of direction of optimizations your solution was, and of course Alex is yours also. I'm still gonna try to solve it myself first, of course, but most likely I'm going to have to ask for some hints pretty soon. It's 5 19, it means that we have 40 minutes left. You were so excited when you came up with a faster than brute force solution. And it kind of wore off when you realized it took an hour to run. Wow. Wow, yeah. I can imagine that. Yeah, if you manage to solve it within 1 hour of running, that is still alright. I guess you can just wait for the output, but that means you have to see the first phase completing within a reasonable time, otherwise, yeah. Otherwise you don't know how long it's gonna take. But if you see it complete in 1 minute for one phase, you can just keep it on for like 100 minutes and it would be fine. And Alex, you're thinking that all solutions are the same. That can be true, of course. Well, basically, I could look up fast Fourier transformation and see how that works. I'm not sure if it's cheating, but let's look at it. There is a trick, yeah. So you see, really, it looks so similar. You're combining all of the numbers with other numbers. Okay. And there are some algorithms like the Cooley-Tukey algorithm. Divide and conquer. And it breaks a DFT that is a discrete Fourier transform, I think. Though I don't know what that means. Yeah. I don't know what that means, but I do know the word. It breaks it into many smaller DFTs. Yeah, I was thinking about something like that also, that you can break it up, but I wasn't sure how that would actually make it faster. So I'll start, I'll keep going on with what I was doing right now. So I'm gonna write it vertically instead of horizontally. So we have A times A1, B times A2, C times A3, and D times A4. That is the first digit. And let me just put it in a nice position. And the second digit will look like not ABC, but we will have D for that pattern. Wait a second. No, we still use A, B, and C for calculating the new digit B, but we're multiplying it instead with the patterns for B. So it's B1, B2, B3, and B4. B4, huh. Okay, so we get the same thing for every digit in the input list. And I already see right now that there are no repetitions in the first phase. So within a single phase, it looks like you don't really get a repetition, because you see that here you're multiplying everything with B1. But of course, well, there was something else that I was thinking about, because basically you're doing like plus A, minus A, plus A, minus A, because all of those values in the patterns are like just ones and minus ones and ones and minus ones, and some of them are 0, so the zeros you don't actually use. So in the end, you're just adding a whole lot of numbers, and you can probably just kind of figure out how many plus ones and how many minus ones you have, and then take the difference and then see how many times you need to have A in this position. And maybe that's something we can try to do. So first let's look at the first iteration of this very tiny example. So for the third digit here, we're going to use C1, C2, and 3 and 4. And let's see if I can move that. We don't have a lot of space with so many numbers. And the last one will also be in a similar fashion: D1, D2, D3, and D4. Now, so in this phase we don't have any repetition, but maybe when we go to phase 2 we do get a repetition. Let's see again. Let's still look at phase 1 a little bit. So phase 2 is going to start there. And let's see if we have anything that can help us. I'm going to enable zooming in a little bit so that it looks like this. And I'm going to write very tinily what those values actually were, maybe in bright color. So this list was actually 1, 0, -1 and 0, and this list was 1, 1, 0, 0, -1, no, hold on, 1, 1 and 1, and 0, and all ones. The fact that the last column is all ones might help. That might help very much indeed. And how it would help is that once we know the entire last column, basically the column to the left of it here is actually the same as the previous one, except this one is not included in it. That is the case, in fact. Yeah. So we could start by first making a sum. But, how does it work? What happens if we have a whole lot of digits? Oh. No, what I'm doing is definitely incorrect. I have made a mistake. Because the patterns for D are not only ones, they are mostly zeros and then one single one. So let's see if we can correct it. So let me rewrite the patterns here. But I think this is something that might be useful though, to look at it this way. So D has 3 zeros and a 1. And C has 2 zeros and 2 ones. And then B would have 1 0 and 1 1. Is that right? And then another one, and then one more 0. Yeah. And I'll just rewrite this base pattern a little bit bigger. So it would be 1, 0, -1, and 0. Now, what do we see in here that we can use? What do we see? This matrix, I think I will just take it out. So the last one here, the last pattern, that contains only D. And the one to the left of it is basically the digit to the right, but also we add this value here. And then when we go to the left, so far at least, we would basically add to that. Oh no, wait a second, we're adding this value. That's the additional value. And here we're adding this one, but we're subtracting this one. So this is like, let's say plus. I'm not sure if this is going anywhere, but who knows. Plus and minus. Then when we go to the one all the way on the left, we're going to add this one to the previous calculation. And well, we're going to add that one, and we're going to subtract. Oh, it's actually quite different now, because first we had 1 of this B, sorry, 1C, and now we're gonna have -1C. So we need to subtract it twice. That means, oh yeah, I think that the way I'm marking my boxes right here is not that correct, because the patterns start here like this. So for the second pattern right here, we're going to have to add this box and subtract this box. Well, the one from the previous iteration. No, hold on. Right. I think it's a matter of adding the B and subtracting the D. Yeah, not the full multiplication. So this one is the plus and this one is the minus. And then for the next step, this one will be plus and let's see, this one will be minus also, I guess. So that means that we can relatively quickly calculate everything if we go from right to left, but probably you could go from left to right also. I don't think it really matters. But now something that I'm definitely not sure about is what happens if you have a lot of digits. So you have a much larger matrix than before. So I actually want to visualize that and see what we would get out of that. So a huge multiplication matrix. Maybe that's why Anthony was printing the matrix on the screen. He was printing it in a very huge font in the terminal and looked at it. Well, maybe for now I'll just start by writing it out. So we have all the zeros here that are going to be ignored. So I'll just write them out, and let's use 8 digits for now. And then it's 0, 0, 1, minus 1, 0, 1, 0, minus 1. Okay, we need to have at least 8 of those, yeah. And then the second one will have 2 zeros. So it will look like this. This is a bit boring, but I think it is handy. Like this, more zeros. Just to get the screen filled. And one more, and one more. And then I guess I need to add another one because we're skipping the first line. So here we have another 0. And then after that follow all of the ones. So 1, 1, 1, 1, and 2 ones, and then 3 ones, and then 4 ones, and then 5 ones. Basically, from this point on, it's all going to be filled up. And then we have zeros, 2 and 3 zeros. Then we have minus ones. Okay. Well, that is the matrix. It's not very square, but it is a square. And hold on, why is our last matrix completely empty and it doesn't have any zeros or any ones? Let's see. So this first line is going to be skipped. Then we're going to have line 0, 1, 2, 3, 4, 5, 6, 7. We do have 7. I see what I did wrong. I accidentally misaligned my writing. So here should be a lot of ones, and then I have to remove 1, 1 out of that list. Or actually, hold on a second. We have 1, 2, 3, 4. Okay, so this should be a 0, and then the rest is still going to be the same. Now I hope there's no mistake in there, but I think it is mostly correct. So yeah, then it does make sense to start with this one here, then add this one, then add, add this one. Oh, but actually, I'm thinking now, so what we're calculating here is the new A, right? This is the A column, B column, C column, and D column. And wait, this is just a pattern. This is not this. Oh, I drew the wrong thing. Like what you see here Wait, that is the same thing. That is exactly the same thing. I just need to write down the fact that this is a multiplication and that on the left we also have A, B and C. So basically this is what it looks like. Oh, wait. No. So, yeah, it's correct. I should just draw the other letters also. A, B, C, D. Thanks Alex for pointing out that I'm on the right track. That gives me a lot of confidence to continue and hopefully to get somewhere before the end of day 16. So, alright, once we have calculated the new H digit, then to calculate the G digit, all we need to do is basically do H, let me write it down clearly, H plus, yeah, this thing here. I don't know how to call it. It is basically, well, what it is a multiplication of the G value with the pattern of for a particular, with the pattern. Man, this is so confusing because we have the input digits that go like this, then we have the patterns that go down, and then when we're calculating the G digit here, we are using all of the digits also, but we're using only the G pattern. And so, yeah, okay, in this list I'm showing which elements of the G pattern are going to be used for every other digit in the input. Yes. So for G, we say we're only using the G and also the H. So yeah, it really does say literally G plus H. That is kind of funny. So G equals G plus H. And F equals G plus F. Well, okay, maybe I should give different names to G and F. So it's like the HN is calculated here, and then here is G plus HN. And here we're calculating GN plus F. And then here it's E plus FN. FN means F new, like the next one, the next F digit. Okay, so far so good. Here we can say it's D plus EN minus HN. It's going to be hard to fit everything here. Okay, that still works. I think I probably did make a mistake in my matrix. I'm not sure if this looks correct. 1 0, 2 zeros and 3 zeros. Yeah, it looks right. Okay, and here, so this one we did a minus this last. I found out I have a laser pointer on this thing actually. So this thing we subtracted, and then. So for C, we're going to use dn plus C minus en. Okay. Well, if that is how it works, that is very simple because we just look one to the right and subtract it. But it's not one to the right. So for the case of D, here this column, we were able to just take the D value, add to it all of E, and subtracting from it HN. Maybe that is not really the way to go. Maybe, well, maybe it is the way to go. That depends on how the pattern evolves, maybe. Maybe it's something we can figure out once we go a little bit more to the top, because that is where the base pattern is repeated multiple times. And then we can see actually if we should subtract from the right side like the sum of the digits of that whole column, or if we should subtract only the single value of the previous digit. That is something that I'm not sure of right now. So if we are comparing D and C, these two lines, then we do see that C is the same as D, but actually it's minus, yeah, all of these values. So we cannot just subtract. We cannot do like C equals D minus E. That wouldn't work, because then you only subtract this particular value here, and that is not right. We need to subtract, oh, not this part, we need to subtract this part actually here. So it is going to be D minus F, right? Plus C. Okay, let's see. So the basis is always the letter itself, C, and then plus the previous one, Dn, and then minus. But what I was saying here is that we're taking this one and then doing minus F. So that's like one further than the previous one. That makes it a little bit less handy, I would say. So minus Fn. And now I want to know, in the other cases here on the bottom, did we do the same thing? So the base letter is C, here it's D, here it's E, and then in this case I wrote F on the bottom for some reason, and here we have G. And when we are subtracting, we are doing here F, and here we subtract H. Oh, and we're not subtracting anything here. That's interesting also. We're not subtracting anything here at all. I'll use a wiggle, like a little tilde, to indicate that we're not subtracting anything. So F and H are not neighbors, because G is in between. That means that the number of steps we need to look to the right for subtracting is not going to be always one column to the right. It can be multiple columns to the right, and that is a little bit annoying, because that means we have to also figure out how to calculate which column we're gonna subtract. But maybe there is an easier way to do it. Well, we know that F, as I write it here, wait, this F, it is the same, of course, as F is the same as G. Okay, that doesn't really help, but maybe we can say something like F is actually the same as E, but then we just need to add E again, or something like that. If we do that, well, maybe that's not going to be helpful. I'm not sure. I'm going to try to continue this line of thinking with the B column. So to calculate B, what we need to do is to take the value for B, which I was going to draw in yellow from now on. So we need to take the value from B, and we add to that all of the values from the C new digit, which is this part. But then we end up with something that's not completely correct, because then we would get 1, 1, 1 here and 0, 0, 0. So we need to actually subtract this one, and we need to subtract a whole bunch here. how does that work? What can we actually find in this table that would help us achieve that? So I see here we have 3 -1s, so that means that probably there's some place with a lot of 1s, and that is actually F. So we could use F to actually remove those. I do think that I might have done something wrong. Yes, I did, because in column B there should only be 2 -1s and not 3, because it's the second column and every digit is repeated only once. So repeat it twice so that you have it twice every time. And after 2 iterations of base pattern 1, we'll end up with the same number. That is correct. Okay, so we need to subtract 2 1s here, and what we could do for that, actually there's no other pattern in the list that matches that exactly. Wow. Maybe I'm not sure. Yeah, I think I would like a tiny hint. Thanks, Alex. If you can help me, push me a little bit further. Because we have 15 minutes left, and probably even if I do figure out how to magically get out of this, then I still won't have time to actually implement it. And you're saying that I'm missing something. I hope it's tiny. Well, that sounds tiny. And if it's tiny, well, rereading the input or the puzzle is always a good idea, because that could actually save you hours of time, you know. So I'm going to read part 2. The real signal is your puzzle input repeated 10,000 times. Treat this signal as a single input list, yes. Patterns are still calculated as before and 100 phases are still applied. Lol. I think I got it. Oh, I think no, maybe not. Okay, I'm thinking, so actually the first part of the input is going to be a position of a position in the list, and from that position in the list we need to read 8 digits, and those 8 digits are actually the answer that we need to provide. So what I was just thinking right now, maybe we can only calculate those 8 digits and ignore everything else. Is that true? Can we do that? I don't think so. No, probably not. We cannot do that. I'm on the right track. Okay. Well, let's say that we have this one, right? This little example, and we were only interested in knowing a few specific digits, like let's say D and E. But to calculate D and E, we still need to read, in this case, all of those values and all of those values, right? So that means we do have, okay, that actually does help. It does help, because which values we're going to need to read for those digits are going to be fixed. They are going to be fixed. So for D, we need to know D, E, F, G, and H, but basically we can completely ignore all of the other numbers. This feels good. This feels good, guys. Thanks. For E, we can look at only these numbers. That means that A, B, and C are never going to be read at all. That is interesting. Just thinking again twice to make sure that I didn't miss anything. But we know that every digit on every position of the list has its own pattern. So anything else is never used. That is so cool and so interesting. Okay. So if we can calculate the base pattern for D, and then what do we need to do? We have the pattern and we do have to kind of add up all of those numbers, and in that particular way we only have 100 phases, so it's not like you need to optimize for redoing that calculation a lot. You just need to optimize for knowing which numbers to use. But there's one tiny issue, which is that the base pattern has the following numbers: 0, 1, 0 and -1. So that means that if you repeat that n times for D, let's say D is at position n, then you're still going to have this number 25% of times, and this number also 25%. So that means you're still working with 25% of your input. And okay, right. But now I realize something, and that something is that the input pattern is repeated. It is basically a 650 digit long number, repeated 10,000 times. So if it is repeated 10,000 times, does it mean that we can just multiply this whole thing by 10,000 and that would be it? Maybe it is the case. Ooh, let's see. Oh man, this is like really too much. But let's see how it works. I feel like I'm like at 90% of my working memory in my brain right now. But we need to add a whole bunch more. So the input list looks like this, and like this. So that means that yeah, the inputs are repeated, but the pattern is not repeated with the same offset as the input. So if this is like 650 long, it doesn't mean that your pattern that goes down also repeats every 650 times, because the repetitions are like based on the offset. So how much they repeat depends how far you are, like this. So how many times do you actually reuse or doubly use a certain digit? So, well, let's say at position D, yeah, what I do notice, well, what I was gonna say is that from a certain position on, all of your inputs are going to be all of your patterns are going to be all zeros and ones also. So rather than this part where you have quite complicated sums with subtractions and additions, from over the second half, is it from the second half? I'm not sure if you can just say it like that, but from a certain point on, you're going to have only zeros and ones, and maybe that's actually the case. So I want to know what is the input position of our message, and the input position is the first 7 digits of the input, and that's written right here. So those are 7 digits, and our input is I'll just run it and see how can I calculate where that is. I need to know the number of digits in the input, which is of course 600 and wait, was it 640 or 650? 650. So it's 650 multiplied by 10,000, and then our offset is actually this position, and let's see how far that is into Actually, that is at 91% of the input. That means that our base pattern, or our pattern for that position, is actually going to contain mostly zeros. Huh, I see. Well, so let's look at... So, okay, in the visualization, that means we're basically here, like all the way on the right. And so we're going to have like really almost zeros everywhere. And that is going to help a lot. Why was that helpful again? Because it means that we don't have to actually pass so many digits. The number of digits that we need to handle for that position is not that much. So I can basically first calculate the pattern for the position, the first digit of the message, and then once I have the pattern, make a list of offsets that I do need to use, and then iterate over the offsets, and then take the digit from the previous input and just add them up. That's it. Huh. Wow. Okay, well, day 16 is almost finished, and I'm not gonna be able to implement this on time, but I want to take the last few minutes to make notes for myself so that I actually remember what I'm going to do. So thanks for staying with me here and giving me that tiny little hint of reading the input, or reading the instruction. I think the key is that message thingy. And so that is a completely different direction of how to optimize the puzzle actually. So you're not actually numerically optimizing it very much, you're just optimizing it for your specific case. Yeah, I might have figured it out, but I think I might have spent a lot more time looking at how to optimize the complete calculations instead of just the part that I needed. So what we're doing is we're looking at the positions here, and we're going to see that for every digit here we need only very specific inputs, and so it would look something like well, the zeros, they kind of go like this, so that means mostly we need... Oh, actually I just realized that the ones that are in here are in fact the ones from the message. That's crazy. So actually we don't have to calculate anything outside the range of the message. Ah. So actually, we basically have a matrix with only zeros on the top and only ones there, and our message is here, and our message is also here, and we can just run the DFT or the FFT only on the message. That means I can actually solve it. I think so, but I just need to use different patterns. I just need to use different patterns for this case. Okay, well, in that case, I'm just going to skip over all of my code, and I'm first going to extract the message from the input. So this is the input, and we're going to get the message out of it, and I've already made code for that. So we have the message offset, we can use that. Oh, wow. So let's get the message out. It is this little piece. I'm just going to skip over it and see if I... wait a second. This is how I wanted to print it. So I'm printing it, but the message is calculated here. Hey Emily, good morning. You're just joining in right after my figuring out of how to solve part 2. I haven't actually solved it yet, but I'm quite close. So let's run this and see. In fact, my old code was still processing. So we have the message offset. Wait, why is my offset so complicated? It's just the first 7 digits, right? Huh. That is a bit hilarious. That is a bit hilarious. Okay. The message offset looks like that. Let's run it. Time for day 17. Good luck, everyone. Yes, we are starting right now, so good luck. I'm going to finish part 2 of day 16 and then continue. See you very soon. So our message offset is printed right here. Those should be the first several digits, yes. And then we need to take the message, and the slice is not exactly correct. So the message offset, let's make it into an integer, of course. Now we do get the numbers that we need, and let's... Yeah, that was it, huh? Wasn't it? Yeah. So the input digits can now be written like this. And that's it. So I can actually use the same thing, but I don't need to use the patterns as they were. So, okay. So how do we do a phase right now? So for phase in range 0 to 100, we're going to repeat. And the output digits are going to be a copy of the input digits, like this. And maybe I'll actually make them into digits. So int d in d4. For d in the input digits, now we have a list of digits. Then we need to know the position. We're going to iterate over all of the positions. So let's P and D in enumerate. No, actually we just need the position. Or not. Let's enumerate the output digits. Yes. Okay, then we have the position and the digit that we're working with. Not sure if we really need the digit right away. And then the new digit is 0, and we're going to add everything from the output digits that we had from the start till the position. That is going to be what we're adding. And that's basically it, isn't it? The new digit is a sum of everything from the left till the right, modulated by 10. Because, let's double check it, we have this matrix with A, B, and C, A, B, and C. Here we have ones, and here we have also ones. So to calculate A, we need everything from here, and for B we need I should look from the top down. So for A actually we sum everything, and for B we sum everything except, well, it's basically the new. We could do it like this. We could say it's A minus A. It's the new one for A minus A, and for C it's basically the new B. New B minus minus C. No? Minus B. Yeah, it's basically this one minus this one. Okay. So the new digits, let's write them down here. It's an empty list. And then let's see how we can do it. So if position is 0, that's the first one, then new digits 0 is going to be the sum of all of the output digits from the previous phase. And otherwise, we're going to append the new digits first previous position, so P minus 1, and then we're going to subtract from that previous digit also from the previous phase. Does that make sense? Yeah, so minus the output digits position on the left. And then we need to do modulo 10. No, not modulo 10. We need to keep only, yeah, modulo 10. So we have basically the last digit. And here we also need to do that. Wow. And then we just continue that. But after doing that, we need to override the output digits with the new input digits. Or new digits, like this. And then we continue. And then we're going to print the output digits. I don't think it's going to be correct right away. It would be very easy. Well, maybe it is easy. So let's join the output digits. Oi. Oh, it must be strings. I don't like that. Python, come on. So we need to do string on every digit for D in output digits. For D in. Okay, now we have something. We did run it 100 times, I think. I don't know. No, it's not correct. It's too high. So let's return. I'm writing down too high. I guess I want to debug this a little bit. So let's run it. And so the first digit is 0. And we have our input digits like here. So the first time we're going to calculate it is basically the sum of all of those digits, which I think should be correct. But the sum of all of those digits, oops, is going to be 40. And that means that we get 0 as the first value. Can that be? Maybe that's what we get. Yeah. So we get 0, and then for the next iteration or for the next digit, we are going to use 0 minus previous one. I'm not entirely sure that actually is correct. I think probably what we need for the second case is using all of the output digits and starting at position B actually until the end. Then we get this, and we're gonna sum that one. Ah yeah, of course we cannot just do modulo because we're throwing away the sum. We should modulo it in the very end. Oh Alex, you've already solved part 1. Oh my god, that is so fast. That means it's probably also a simple puzzle. That is good news. I am not looking forward to a long puzzle again. So the output digits are going to be every digit in the new digits that we calculated, but we do modulo 10 for D in, right? Let's run it again and see if that gives us a different number. It does. No, it gives us the same number. In fact, how is that possible? I'm printing only one thing. So since we already tried it, there's something not going right. Okay, debug mode again. We do the first iteration, first phase, first digit is now done. And now we're going to calculate the second digit. And I was saying to calculate the second digit, it's basically the whole column of input digits on the left of it. And let's see. So the one on the left is the new digits of P minus 1. That should be 40. And then we're removing from that the current... Wait, is it the current digit? Let's look at the diagram. So you have basically so from B we have everything from the A column except for the value of A, so 1 times A, and that is the first digit of the phases current input. Current input means actually output digits. That is a bit confusing. Maybe that's why I better rename it to phase input, like that. And then new digits is going to be called phase output. And not sure why I cannot use refactoring with my keyboard. Phase output. Right, that makes more sense. And then let's run it. So we now have calculated the first digit, and you see it's 40. And then for the phase output, then we're going to take 40 minus. Stavoy has finished part 1 also. Well, it's going well. And that was 7. Okay. Yeah, that seems fine. And then we're going to just get 40 minus 7. So that means that our phase output should now be 40 and 33. That is fine. And we're going to repeat that until we reach the last digit. And then we get the following phase output. And we're taking modulo 10 for every digit. And that looks like this. Okay. 0, 3, 1, 3, 5, 2, 1, 8. Not sure why it's incorrect, why our output is incorrect. Maybe I am making a wrong assumption about the 90%. So I said in my... yeah, we were looking at the message offset. Oh yeah, and there was something about... The message is how much you should skip to the right, but I think we're doing it right. We're starting really from the offset. So if the offset was 0, we would start at the very start of the input. So we shouldn't skip the message before skipping to the offset. So that part is fine. And then we're taking 8 digits from there. Am I running it on the right one? Yeah, I'm running it on the real input. And I'm running it also 100 times. I am kind of sure that it's running 100 times. Let's say we do range. Well, I know range is exclusive and it starts at 0, so it would, if I would make a range of 0 and 1, then it would repeat only once. Let's see if that is correct. So after one phase, the output looks like this. Basically, maybe I can copy it. Yeah, I can copy it. That's handy actually. So if I would run it just once with, yeah, then I would get a 0, a 3, a 1, a 3, a 5, 2, 1, and 8. So our range logic is also correct. Yeah. Okay. Repeating the input signal 10,000 times and 100 phases. What's the 8-digit message embedded in the final output list? Yeah. Of course, your real message offset will be a 7-digit number, not a 1-digit number. Am I taking 7 in my input? Yes, I am taking 7. From 0 till 7. And we have 7 here also, so I'm sure that is fine. And then, yeah, I was saying, so if we are over the halfway point of the input, then basically all of our patterns are going to have 1s and 0s. That's all. So let me just use another color here again. So over the halfway point, we only have 0s and 1s. But it's not necessarily so that... hold on a second. So for... Oh yeah, but it is actually true that if you look at only E till H, for example, then you do get this matrix that looks like this. And no matter at which digits you're going to look at, like let's say we're looking at F, G, and H here, then we're also getting the same matrix with ones on the bottom and zeros on the top right. So I think my matrix is also correct. Now the only disadvantage right now is that everyone is starting on day 17 part 1, and so there's no one here to help me out if I am on the wrong track. But I've been encouraged multiple times that I am on the right track, so that means that this is really right, and I'm not sure where to go from here. So if we run everything, we get a number here. Oh, wait a second, I am doing phase input here in the end. Is that fine? I guess it's fine. Yeah, let me just print it, just to get an idea of what we get as an output. Well, that's a whole lot, and now my question is, why does 8 always stay 8? That is a bit suspicious, so maybe I am actually missing the calculation of the last digit. So if we start with this one here, that means that no, it is correct. So if you look at the matrix, the multiplication matrix, and you have a grid like this, well, the matrix looks like this, and let's say it's 4 by 4, then we have 1 1 1 here, 1 1 1 1 1 1. So for D, the last item in your list, you're always taking only itself and not anything else, so that number will not change. That is correct. And so the second number from the right, that one will always be itself plus the previous number. So that is very easy to verify by hand, with a bit of staring involved. So that means that if we look at this number 1, then the next time we're going over it, we should have the number 1 plus the number on the right, which is 8. So it will become 9. That is correct. And then it will be 9 plus 8. It will be 17. But we're chopping off the one on the left, so we get a 7. So that actually does look like it is correct. And I do also see a repeating pattern in there, by the way. It's like 19753, 19753, and so on. Just keeps going. And that is how we get the output, but it's not correct. And we did run it 100 times. So if I select it till the very end, we do say that we have 101 line breaks. Oh, and that's because I'm outputting the final output another time. Okay, so we went over it. Yeah. And I don't see where I'm going wrong. Maybe something about the offset. I don't think so. And also, I am noticing that I am really having a hard time to stay focused. I did wake up again at 4 AM today to try to do this. I am going to park day 16 for now, and I'm going to have to continue on day 16 a little bit later. I'm going to take a mini break, just like 5 minutes, and maybe have a little bit of food, and then going to work on day 17 part 1. I'll keep the stream on. Do check in once you're done, or once you're ready to have a look. See you in a moment.